Hello and welcome to this Thought Labs CMP on-demand lecture on heating systems. This is given as part of the construction technology module. My name is Robin Escobedo. I have 10 years experience in the industry. This is across a wide range of sectors, from healthcare to education, industrial, commercial, residential, etc. So in terms of heating systems, I've worked across the board really and hope to share some of this experience with you in this lecture today. I also have a master's in building services engineering. So in this lecture, we will be going over heat transfer types, passive reduction, heat generation, heat distribution, and design considerations for heating systems. The first point of call in any heating system design is to find out what heating levels we need to provide. We do this by first calculating what heat loss we must overcome. Heat can be lost from a building in a combination of four ways: conduction, convection, radiation, and infiltration. Conduction. When one part of a solid absorbs heat energy, the atoms will vibrate faster. These vibrations pass from atom to atom, energizing the other atoms and transferring the heat energy along the solid as they do. This is known as conduction. So, when the solid is heated in the picture, the red atoms are the hot atoms and they will vibrate. Eventually, they will vibrate adjacent to the blue atoms and they will pass on the heat energy to the blue atoms, which will also then vibrate. This will continue throughout the solid. Conduction will continue throughout this solid. If you consider this in a building scenario, one side of a window may be heated, whereas the other side, especially on a winter's day, may be cold. Conduction would occur through both the window and the window frame. The heating system in a building will need to account for this heat loss in order to overcome it and ensure a comfortable ambient temperature for the occupants. A way for designers to reduce heat loss and hence reduce heating system demand would be to include a thermal break. This breaks the conduction cycle by including for something that isn't a solid within the construction build-up. For example, in a double glazed window, there is a gas break between the window panes. Conduction still occurs through the frame, but it is greatly reduced as it cannot pass through the gas. This heat loss and the demand on the heating system would be less than for a single glazed window. Next is convection. Convection is the flow of heat from high to low temperature in a fluid. If you consider the figure, the air close to the radiator will get hot. As it heats up, it will become less dense and rises, pushing the cooler air beneath it. Then, as it cools, it becomes denser and starts to sink. This is shown near the window. This process results in a cycle, what we call a convection current. Radiation occurs via electromagnetic waves, and these can occur through any medium, including vacuums. Heat will transfer from any object that is of a higher temperature via radiation. For example, if our bodies are of a higher temperature to our surroundings, then heat will radiate from our bodies. If you consider the image of a radiant heating panel, heat will be transferred via infrared rays from the panel in all directions. It is important to note there will be a small amount of convection also, as the panel will cause the air surrounding the panel to heat up and become less dense. However, the majority of the heat transfer will be via radiation. And finally, we have infiltration. Infiltration is where air is introduced into the building via leakage. This could be via cracks in the building fabric, for example. The cooler air in the winter will introduce drafts into the building and lower the temperature. The heating system will need to overcome this. The two main types of heat loss that occur within buildings in winter are via conduction and infiltration. The heating system needs to be sized to overcome such heat losses, and hence reduced conduction and infiltration rates within buildings are one way of getting a reduced heat demand. This could be done via using materials with lower U values. For example, a double wall with foam-filled cavity has a U value of 0.5, which is a much better thermal performance than a single brick wall that has a U value of 3.6. You could use thicker building materials. For example, the wall that's double double with foam-filled cavity will be a lot thicker than the single brick wall. This will give a greater distance for heat to transfer through, and so conduction will be slower. You could ensure all penetrations are adequately sealed, for example around incoming pipes, and you can treat any barriers between heated and unheated spaces as external doors, so you would require to put the same level of sealing around these external areas. If we can quickly consider cooling, the opposite will occur and heat will pass from outside to inside on a hot day. The same in terms of reducing losses is applicable to cooling. However, we also need to consider the effect of radiation and ways of minimising this. This could include using windows with lower G values or looking at shading techniques such as brise-soleil. Brise-soleil will shade the windows and reduce the radiation passing through the windows. Types of system. Generation. Boilers can use a range of fuels such as natural gas, LPG, biomass and oil, natural gas being the most popular. Advantages of boilers are that they are space efficient. If you look at the figure in front of you, you can see boilers can be stacked. If a combi boiler is used, then there are no need for hot water tanks. They are capable of providing heating and hot water instantaneously. This does come with a caveat. If there is a building that has a high hot water demand, for example a leisure centre where there may be 5 or 10 showers running at once, then even a combi boiler is unlikely to instantaneously provide the hot water demand. Therefore, a hot water tank would still be required. Boilers are relatively low cost. They are available in a range of sizes. We have them in our homes, they are in industrial units, they are in commercial units. Maintenance is readily carried out on boilers as well, which is another advantage. Boilers may be modularised, so in the figure in front of you, you can see there are 4 boilers. To consider the implications of this, we shall imagine that this building has a 400 kilowatt heating load. If one boiler was used that had an output of 400 kilowatts, then even at times of low demand, e.g. 60 kilowatts, that 400 kilowatt boiler would be running. Because boilers can be modularised, at times of low output, e.g. 60 kilowatts, if each of these boilers was 100 kilowatts, then only one of those boilers would be running. This would save 300 kilowatts. Another type of boiler is a biomass boiler, which uses biomass as opposed to gas. This could be in the form of wooden pellets, biofuel, or even bio-oil. The UK government recognised that biomass is a cleaner fuel and offer it under the Renewable Heat Incentive Scheme. This is a scheme that makes payments to participants that generate renewable energy and use it to heat their buildings. For example, if the client decided to install a biomass boiler that used solid pellets and he utilised it, then he would receive incentives under this government scheme. Biomass is often a byproduct or a waste product. Therefore, these pellets, for example, would otherwise be going to landfill. By using it in our application, we are saving the pellets from going to landfill, and so we are reducing the landfill in the country, which is good. It's already absorbed carbon dioxide during photosynthesis when it was a tree, meaning that any carbon dioxide produced during burning is already offset. Again, biomass boilers are bigger than standard boilers, as they also require storage for the biomass. In applications where space is a premium and the client may not want to give up lettable space, or they may not want an unsightly biomass container in their car park, or there is not space for an unsightly biomass container anyway, then this might not be feasible. Also, if there's no local supplier of this biomass, then the carbon and logistical implications of transporting the biomass need to be considered. For example, if the biomass was being delivered and it couldn't be delivered because there was snow and it was unsafe for a prolonged period of time, then this building would be without heating at a time when heating was most needed. To get around this, usually a boiler is provided to give resilience to the biomass installation if the supply chain failed. However, this again is an additional cost, it's additional maintenance, it's an additional installation, it's additional space. So, an alternative would be ground source heat pumps. These transfer heat from the ground. Ground source heat pumps are connected to a series of pipes which we call ground collectors. These are the red and blue pipes you see in the garden. These are laid in horizontal trenches like the photo or in vertical boreholes. And at depths under the ground it is hotter. It's around 10 to 12 degrees. It doesn't matter the time of year. So within these pipes we have a water refrigerant fluid which we call brine, and it absorbs this thermal energy from the ground and it circulates it back to the heat pump. A compressor inside the heat pump increases the temperature and passes it to a heat exchanger. This transfers the heat to hot water cylinders, radiators, your emitters, and basically this is your space heating and your hot water for your building. Once the fluid has delivered the heat to your building, it's passed through an expansion valve, so it's cooled, and as you can see it turns blue, it goes back out again, and the cycle continues. Advantages are it's incredibly energy efficient. Efficiencies are up to 400%. They require less space within the building, that's not really too noisy, and it can do both cooling and heating. However, this ground loop does take up space, and so it might not be suitable in retrofit, urban, or space limited installations. For example, if you are building in a built up area where there are already utility services, way leaves, foundations all around you, then it is unlikely that you will be able to dig a ground loop. Furthermore, any maintenance issues with the ground loop itself need to be considered. For example, if you built a car park over this ground loop and you laid a big concrete slab for your car park, and this ground loop required a repair in 10 years' time, then you would have significant disruption in digging through this concrete slab and digging into the ground to carry out the repair. So another type of heating system to consider is air source heat pumps. Air source heat pumps work on a similar principle to ground source heat pumps, except they transfer the energy from the air to the water as opposed to the ground to water. An outdoor unit draws in heat from the ambient air, which is number 1, and it blows it over a heat exchanger coil. Number 2. This has a coolant flowing through it, so the heat from the air is transferred to the coolant. So the coolant is turned warmer, and as it heats up, it turns into a warm vapor, which passes through a compressor, which is number 3. This compressor increases the temperature and compresses it to a dense vapor, which is number 4. This hot coolant vapor transfers to the indoor units through the internal piping systems. Again, it's showing you as number 4, your hot vapor. And then the indoor unit blows out heat from the coolant to the indoor air via fans. So once your hot vapor gets to your unit, it blows out the air and heats the room. Once the coolant has transferred some of its heat to the air, it cools back to the liquid. As you can see, it's going to purple. Passes through an expansion valve. Again, this reduces the temperature. It lets go of more heat. And this cold liquid vapor, which is now your blue and white line, is then circulated back to the outdoor unit to be heated again. Advantages include the fact that they can be retrofitted. There's no ground loop. However, they usually need an external compound to house the units. This external compound, however, can be anywhere around the building as long as there is a route back to the building. It doesn't have to be in a specific location. Maintenance and installation costs are much simpler because you're not digging into the ground. However, a real big disadvantage of air source heat pumps is they require a significant electrical supply. This will increase the electrical demand in the building, and if retrofitting, you need to ensure that the supply to the building has capacity and the distribution boards have the necessary ways in order to accommodate the heat pumps. If each heat pump is 63 amps and a medium-sized building has 3 heat pumps for heating and 3 heat pumps for cooling, that is over an additional 300 amps, which is a significant amount. If the building does not have that capacity, then you might have to apply to the DNO to increase the supply, which could have a significant cost. Also, the DNO could reject this if there's not the capacity within the area. You also need to ensure that your distribution boards have the necessary ways that would supply these air source heat pumps, and if not, you might have to change your distribution board to different boards that have additional ways. If hot water was generated with any of the aforementioned methods, it would be part of a centralised system. This is shown under the shower and bathtub, and you can see the square boiler, and it's a centralised system because it's one central boiler providing hot water to the shower, the wash basin and the bath. To ensure that hot water is available should multiple outlets demand water, a tank may be used in bigger installations. Obviously, this would have a space, cost and maintenance implication. Pipework is also required to distribute the hot water to the various outlets. But hot water can be independently generated at point of use. As you can see on the right, these 2 kitchen sink and wash basin, these are independent generators of hot water. However, they will still need a cold water supply. This would be particularly useful in, say, a building with a large footprint where outlets are some distance from one another. A small amount of space at each outlet, usually in the cupboard under the sink or on the wall above the sink, will be required in addition to an electrical supply to each outlet. Heat distribution. Radiators. Heat can be distributed to rooms in a variety of ways, and radiators are probably the most classic example of this. They're readily available in the designs of different shapes and different sizes, and some can even be custom made to suit, like the image in front of you, which I think is quite nice. Increasing the heat output for radiators does not necessarily mean a bigger wall area. Panel radiators come in single, double or triple panel. As you can see, single panel, single convector, double panel, single convector, double panel, double convector. Therefore, radiators can use a reduced wall space, but their depth would increase. Wall space would still be taken up, however, and this may cause problems in space-limited rooms or on escape routes where clear distances need to be maintained. Radiators also get hot, so they might not be the most suitable option in schools or hospitals, etc., where you have young or vulnerable children and adults. There are low surface temperature radiators that can overcome this, but as they are lower temperature, they will need to be a lot bigger. Radiant panels. Radiant panels are metallic panels with either a pipe that carries hot water over the panel or an electric heating element to heat the panel. As the panel usually gets very hot, they are generally placed at high level. As you can see here, the panels are integrated into the light fittings. So the light fitting is the central, and on either side will be the radiant panel aspects of that. There are diverse applications for radiant panels, with them being able to be suspended directly from ceilings, So, as you can see, installed within walls or ceilings, or installed within suspended ceilings as little ceiling tiles. An advantage of radiant panels would therefore be that space isn't taken up, they can fit in with aesthetics, and there'll be none of the implications on escape distances like there is for radiators. Similarly, there'll be no implications on furniture layouts. However, they will need to be coordinated with the lighting design. For example, if radiant panels weren't an integral panel with the lighting in this installation, then the electrical engineer and the mechanical engineer would have to converse with each other to make sure that there are no clashes between their proposed designs. Occupants may also report hot head cold feet syndrome if the panel is heating their head first if they're too close to the panel. Therefore, the sighting of these need to be carefully designed. Convectors. Convectors can be wall mounted, or like radiators, they can be located in flexible locations, and in the case of the picture in front of you, this is floor trenching. These generally consist of a casing with openings and a hot water pipe. This creates an upward convection current of hot air within the casing. Room air is pulled in at low temperature and hot air is pushed out the top of where you can see the grill bits. An advantage of them is that they provide a high heat output per unit and have a warm-up time faster than radiators. Therefore, in buildings where they are intermittently occupied, for example, in meeting rooms which might only be occupied 2 hours a day, or where in classrooms where there might only be a class every 3 hours, then convectors may be a good choice. Unlike radiators, these can be placed in contemporary buildings adjacent to the glass because they are entrenching. However, as you can see, the casing has holes in it, so it can accumulate debris, and so it will require regular cleaning and maintenance. Furthermore, because it is trenching, and this isn't applicable to all convectors because convectors can be wall mounted, furniture may get placed above them, so this will obviously inhibit their output. Underfloor heating. Underfloor heating can either use electric cabling or hot water running plastic pipework beneath the screed to heat the floor. So in this picture here, you can see the plastic pipework and then there will be a screed on top. A wide range of floor coverings can be used within the installation, so it can match the aesthetics of the room. It can be used in a kitchen where a hard floor may be used. It can be used in a lounge, etc. There is a relatively even heat distribution throughout the floor, and the temperature is not hot enough to burn your feet. So it's much safer and much more appropriate to use these in situations such as schools and healthcare where there are vulnerable occupants. However, in situations like offices or receptions where there's floor boxes and trenching that are providing power to remote desks, power to sign-in screens, etc., then underfloor heating may not be the most suitable, as it may clash with the dado trunking that's providing the power and the data. Due to the low temperature of the flooring, it's slow to heat up, so in intermittently occupied spaces, for example the meeting rooms or classrooms that we've just discussed, underfloor heating may not be the best option. However, in places such as a nursery, where there's both young children and they are in the room from 7 in the morning till 7 at night, underfloor heating may provide a viable option. Fan coil units. A fan coil unit comprises a fan, heating coil, cooling coil, and air filter. The fan draws air through a heating coil for heating and cooling coil for cooling. This air then passes into a plenum, which has multiple outlets for connection to multiple diffusers, or to one diffuser. An advantage of fan coil units is that they are fast to respond and so will quickly heat and cool the space. Again, we go back to our classroom or meeting room. Fan coil units may be the solution. They can be situated above suspended ceilings with grills simply at ceiling level, so again, aesthetics are not too affected by these fan coil units. However, ceiling void depths will need to accommodate the fan coil units, and they do require filters, and these filters need cleaning, and a condensate pipe will be required. However, this condensate pipe is usually small, and it's just to drain the condensate that would be produced from the cooling element of the fan coil. Design considerations. The primary consideration when designing any heating system is compliance. There are several pieces of legislation that we in the UK have to comply with, such as the relevant BSCN codes. An example of this is BSCN 12828. This dictates the design requirements for water-based heating systems. An example of such is that it dictates exactly what timing controls are required for the systems. The building regulations should also be adhered to. For example, approved document L of the building regulations give minimum seasonal efficiencies that boilers should meet in order to be installed within a building. Planning conditions also need to be followed by law. This could be specifying where external compounds or external plant cannot be sited, for example. Finally, sector-specific legislation is also compulsory. This could be in the form of HTMs for healthcare or the output specification for the DFE. An example of this is that pipework cannot run above or adjacent to server rooms, even in the story above, as per the DFE output spec. This would obviously implicate the distribution routes for the heating system. There are also design guides. These should be followed for best practice. These include the Non-Domestic Building Services Compliance Guide, which gives recommended minimum energy efficiency standards for heat pumps, for example. CIBSE guides, such as CIBSE Guide A, give design temperatures for different types of buildings. We would use these design temperatures in our heat losses or heat gains calculations. And further to this is any accreditations that the client is aiming to achieve. These are completely optional. For example, if the client was opting for a BREEAM Excellent rating, there's going to be higher efficiencies, more renewables needed in order to target the sustainability credits. And in addition to legislative considerations, there are building considerations. For example, external space considerations. This could mean that air on ground source heat pumps are not a feasible option, whereas internal space considerations of escape routes may mean that radiators cannot be used. The type of occupant will dictate the medium of heating, and we have already discussed how radiators may not be suitable for the very young or vulnerable because they might fall into them or they might touch them and burn themselves. Further to this, any type of activity within the room will also have an effect. For example, in a quiet room, you don't want to install that noisy fan coil unit. The pattern of occupancy will also impact the choice. Again, we've talked about the intermittently occupied buildings and the fact that the fan coil unit will be much more suited to intermittent occupation, whereas the underfloor heating will be much more suited to the constant occupation. Maintenance of the system will also be required periodically. Consideration should be taken into how this would be undertaken and the likely disruption. For example, if the full building is provided for by a ground source heat pump and this has a problem, then the full building would be without heating or hot water. Whereas, say, there was a modular boiler installation and there was 4 boilers, even if one of those boilers developed a fault, there would still be 75% of the system running. Therefore, the building would still have some form of heating and hot water. This resilience is an important design consideration. Efficiency is also important for both for legislation, sustainability, for cost, and a more efficient system is likely to meet this legislation, have higher cost savings, and represent a much better image for the building. In this lecture, we've covered heat transfer types, passive reduction techniques, heat generation, heat distribution, legislative considerations, and building considerations. I hope you have found these topics useful. Good luck with your preparations for the CMP Open Book exam. Thank you and goodbye.